Okay, so let's start the last session of today. And the speaker is Cristiane Morais-Smith, who's going to talk about quasi-crystals, fractals, and other beauties. And Cristiane, please, the screen is all yours.
Thank you. So I would like to start by acknowledging the invitation by the organizers. It's a pity I can't be there in person. I would have loved to go to India, but maybe next time. So the outline of my talk, I will start with a very brief introduction to quasi-crystals. Then I will focus on the simplest possible quasi-crystal, which is a Fibonacci chain, and tell you a little bit about the cut and project method and about co-numbers, what this is. Then we will look at impurities in the Fibonacci chain and how some order emerges out of random disorder. Finally, we will couple some Fibonacci chains, and at the very end, we will look at what happens if we have a Fibonacci chain. The connection between all the topics and the red line of the talk is, are there connections between quasi-crystals and fractals? These are two very different things. Both are very beautiful, but are they connected in any way? Okay, so quasi-crystals, you might have seen already quite a lot of it during this conference. It was a discovery by Don Schertman when he looked at a crystal, and by doing X-ray, he has seen a symmetry that was tenfold symmetry, which was believed to not exist. He had to fight for very long to get his concept of quasi-crystals accepted. And finally, in 2011, he was awarded the Nobel Prize in Chemistry for his discovery. So this type of tenfold symmetry in X-ray diffraction can arise from aperiodic tilings that you could cover a 2D space, like this beautiful one you see here on the left. But one of probably the most interesting aspects of these quasi-crystals is that they are actually projections of higher dimensional objects. So if you would start from a hypercube in 5 dimensions, and you would do the orthographic projection, you would see that it would come precisely on top of this diffraction spectrum of aluminum manganese. You can see here also with the tenfold symmetry. So they are projections from a higher dimensional ordered structure, although when you first look at them, you don't see much of order into it. So let's then now focus on the simplest possible case, which is the so-called Fibonacci chain. The Fibonacci chain comes from playing with rabbits. So if you now define a sequence in which at each generation, a small rabbit grows into a large one, and the large rabbit gets a baby. So we are going to replace S by L and L by LS at each generation. So here you see as the generation is increasing, and S goes into L, L into LS, in the next L goes into LS, and S goes into L, and so on. What will happen is that the number of letters in each word here is always the sum of the 2 preceding ones. And each sequence, let's say the 13-word sequence, the 13 letters word, is like the 8 letters one, precisely the same, with the 5 one appended at the end. So the sum of 2 preceding Fibonacci numbers gives me the Fn, and in addition, the ratio between Fn and Fn minus 1 gives me the golden ratio. So now I have this beautiful sequence of letters L and S that it's not fully random and not fully periodic. I can build a chain, a tight binding chain with those letters. And then let's say that 2 sites separated by a long bond will have a weak hopping, and sites separated by a short bond will have a strong hopping. I could have also associated on-site potentials to that. So if I take now then the LS, LLS, etc., and I have weak, strong, weak, weak, strong hoppings, I will see that I'm getting a tight binding model very similar to the Sushriff-Higger model, which has strong and weak hoppings alternating periodically. And it's a very interesting model because the Sushriff-Higger model is topological for a certain regime of parameters. And here I have the same structure, but in a quasi-crystalline way, according to the Fibonacci series. I could have instead used the on-site model with weak and strong potentials on each side, also arranged according to the Fibonacci word, and a hopping T connecting all of them. Let's focus here. They are equivalent after a certain step, but let's focus here first on the hopping model. And if I look at the hopping model, I will see two types of sites. Sites like this one, which have two weak hoppings on the left and on the right, which I'm going to call atomic. And sites like this, which has a strong either on the right or on the left, which I'm going to call molecular, because these two are forming a molecule. So atomic and molecular sites. If I now do a different construction of the Fibonacci chain via the cut and project method, I can now start from a two-dimensional grid, which is perfectly periodic. And now I trace a line in this grid, which is starting from one vertex and not cutting any other vertex. It is incommensurate with the two-dimensional grid. And now for a certain range around this line, I will take all the vertices from this 2D grid and project on that line. When I do this, I will get precisely the Fibonacci sequence that I have been just building before, a Fibonacci chain. But now, since I am coming from a two-dimensional periodic structure, I projected in 1D, I got the Fibonacci, but I know that there is still a transverse direction, which is the direction perpendicular to the chain. And something very interesting happens when I now take the same vertices that I projected on this line to get the Fibonacci, and instead I project them in the transverse direction. What will happen is that all atomic sites that I'm here painting in blue, those ones which only have weak hoppings on their left and right-hand side, they will come to the center of this line. And the molecular bonds will come to the sides. So some structure is revealed here from the nature of the sites in the Fibonacci chain, okay? This is going to define something called co-number. If I now look at the numbering of each site in the chain, not according to the way how they appear in the chain, which would be 1, 2, 3, 4, 5, but if I number them according to the co-number order, 1, 2, 3, 4, 5, okay? So this is a very interesting structure that has been proposed before by Massé and Mosseri, looking at this co-number way. So the importance of this projection on the transverse direction becomes now evident when I look at physical properties of my system. So let's write then a first quantized Hamiltonian with a hopping and an on-site that could have for the on-site model the weak and the strong potential wells, or for the hopping, weak and strong hopping. So now I can diagonalize this model. Let's concentrate on the only hopping model with weak and strong according to the Fibonacci. I can diagonalize this model and I can find my eigenenergies and my eigenfunctions. Now, what I'm showing you here, these are the eigenfunctions plotted upon increasing the energy of each one. So eigenfunction 1, 2, 3, 4, 5, which have energies in growing order as a function of the number of sites, because I don't have K anymore. I don't have a periodic structure, so I can't plot spectrum as Z versus K. I have to plot energies as a function of the number of sites. When I look at this, I have the impression there might be some underlying structure that I don't see very well. Well, if now, instead of plotting as a function of the sites in the chain 1, 2, 3, 4, 5, I would do the same plot of the eigenenergies, modulus of psi, eigenfunction, sorry, as a function of the co-numbers. Now I see the underlying order. There is a fractal here in the structure in Hilbert space of the eigenfunctions. And moreover, it's not really a fractal, it is a multifractal, because you see that this little square here in the center is smaller than the outside ones, okay? The centrals here is always smaller than the surrounding one. So this is a multifractal, which has different dimensions, different scalings compared to this box fractal. This would be a monofractal associated to the same structure, which has a fractal dimension log 5 over log 3. So the wave functions are following the same structure, but now with different length scales. Okay, so this is very nice. And can I use this information for extracting any physical information of my system? So yes, and for that we have to use also something that's called a real space renormalization group procedure proposed before by Neil and Nori, because if I now look at the energies as a function of the eigenstates, I will again see that I have 3 blocks, one around 0 and one around the plus and minus strong hopping, and they are again self-similar. So this self-similarity in the energy spectrum can be understood by doing what is called a real spacer G. And in this real spacer G, you start with your chain, you put only the strong bonds, and then the strong hoppings, and you will consider the weak hoppings as a perturbation to it. So when you have just the 0th order Hamiltonian, you have an atomic level at 0 energy, and then this hopping, the strong hopping here, we will split into plus and minus TS energy levels. And on this rough structure that I had around 0 and plus and minus TS comes now a fine structure, which is given by this perturbation H prime via the weak hopping. Okay? So one can apply a decimation procedure to each level, and this decimation procedure will be applied to the atomic or to the molecular sites. For instance, if I start from looking at the problem from the atomic sites, I will do a decimation from my chain by saying, okay, every time that I get 2 atomic sites separated by 2 molecular bonds here, the connection between them I will renormalize to be weak. And if I have 2 atomic sites separated by only 1 molecule, I say that the connection is strong. And I can go on decimating until I cannot decimate any longer. I could have done the same. Instead of looking at the atomic sites and how they will be decimated, I could have done the same starting from molecular sites. To each molecule, I take a central site here, and I say now, if there is an atomic site in between, the connection between these 2 molecules is weak. If there is no atomic site in between, the connection is strong. And I can fully decimate, and I can determine which are the values of these renormalized hoppings, weak and strong. And by doing this perturbative analysis, you will find the values of the renormalized couplings. If you would have, instead of the hopping model, the on-site model for the potentials, you would need one additional step, but it would at the end boil down to the previous model. And it's very nice because now one can, as Nicolas Massé has shown, you can associate renormalized paths to each site. So you started from this atomic site, after the first decimation, it became a molecular site, and so on. So you can have paths by doing the entire decimation procedure. And now let's see what is this useful for, besides being a very beautiful mathematical construction. So recapitulating, we can understand this trifurcating structure using this real space RG. We can find a renormalization path for each side. And we can see that there is a very nice symmetry between the energy levels and the wave functions. But now we can, for instance, ask the question, what happens when we add impurities to our chain? So that's one of the problems that we have been looking at. And this is a work published in 2021. And the first author is Anwar Mustache, who was at the time my master's student, is now my PhD student. And let's look now. This is the structure of the wave functions psi upon increasing energy. And if I would number them according to the real lattice sites, you have it here down. And I am painting in blue the atomic sites, and in yellow the molecular sites, sites that have one double bond as a neighbor. And now we are putting here an impurity in green in an atomic site. So let's first look at the middle plot, where I'm putting here an impurity in green here that looks like just a very banal site. It turns out that if I look at where this impurity is going in terms of the lattice written in the conumber representation, this impurity is sitting precisely at the middle of my conumber chain. And I can see now that this impurity is going to scramble the structure of the wave functions only locally. If instead it is sitting here, still on an atomic site, but a bit to the side, it will scramble the four regions which are around the central one. But the same if I put this impurity on a completely different site in the real lattice, but it is a symmetric site with respect to the center of the conumber chain with respect to the first one. It will scramble in precisely the same way. So I am adding random impurities that if I look at the real space lattice, I cannot see anything that this impurity is random, but randomicity is not as random as we think if we look at it in the right manner. So what Anwar has been showing in his work, we could now also add impurities in the molecular sites on the yellows, and now they will scramble, especially this part of the structure. You see here, if it's right in the center, it will scramble the center site. And on the right and on the left, things are being scrambled the same way, although the impurities are at different positions on the molecular sites now. So it is possible to label the disorder by classifying them according to this real space RG procedure. For instance, if you take a decimation procedure for a certain atomic site or a certain molecular site, that grows from MMMA. And if you put an impurity there, all places where you can put impurities that would be decimated following the same path will have the same kind of effect on the wave functions, okay? So random impurities actually follow a very well-defined procedure to scramble the wave functions of my system. You can see here some types of graphs from the class AMA or from the class AAM, etc. This is MMMM or MMMA. They are different according to the renormalization path followed by them. So this has been all categorized and understood, and everything is published in this work here if you would like to look at more details. So now you can ask yourself, how is it if you would look, for instance, at two coupled chains? We make a ladder of chains, and we can couple them in many different ways, by coupling them uniformly when you couple every side, or by coupling a single side, or by coupling them in a quasi-periodic manner, or by an intermediate site here in between. This work is on arXiv. It's done in collaboration with Malte Röntgen and the group of Peter Schmelcher at the University of Hamburg. So you can rewrite in terms of some symmetry adapted basis, in terms of an H plus, H minus, and some renormalized parameters here. And then you will get this as a direct sum of some positive parity eigenstates and negative parity eigenstates of the Hamiltonian. And you can then simplify if you would do it for some uniform coupling. Not very interesting, but if you do a defect coupling, you will see that there are now states sitting in the gap, and this will map to the problem that we had before with the impurities. You could do also a quasi-periodic coupling, and you will see a new hierarchical structure for the energies. But the potential coupling here, this is a very interesting case where you couple only particles which have a certain VA potential, and now you find coexistence of extended and critical states. So this is a quite interesting configuration to couple and get these states. If you put an intermediate coupling in between the two ladders with an intermediate site, you get something similar to the Lieb-Lattice ladder, which is now coupled here via just the VA potentials, and you start generating flat bands in this quasi-periodic setup. So there is a lot to be played along, but now in the remaining time that I have, I would like to go to a different kind of generalization that we did from the Fibonacci chain, which is the so-called Tribonacci chain. And this is mainly the work of Julius Krebex, who is finishing his master thesis in my group. It is already on arXiv, and the thesis is co-supervised by Anwar Mustaj and Karma Dajani from the mathematics department, and by myself. And here, we are now going to a higher dimensional projection into 1D and find out whether these multifractal properties that we were observing in the Fibonacci, whether they were a particularity of the Fibonacci or not. So let me now start with a Tribonacci word. So instead of small and large, zeros and ones, now I will have 0, 1, and 2. And we will do a substitution that zeros are going into 0, 1, ones go into 0, 2, and 2 goes into 0. So at each generation, I applied the substitution rule for each letter. So 0 went into 0, 1. In the next, 0 goes into 0, 1, and 1 goes into 0, 2. And I keep building that. You will see that we will end up with a word which has numbers which are being now the sum of the previous 3 instead of the sum of the previous 2. This is then a Tribonacci, so the 2 is sum of 1, 1, 0, the 4 is sum 2, 1, 1, etc. Very analogous to the Fibonacci. But now when I look at one sequence, I will see the previous, the before previous, and the before previous being appended here to build that one. Okay? So this is how you build the Tribonacci word. And I can now build in the same way a Fibonacci quasi-crystal and put electrons to hop on a Fibonacci chain. And we can now have 3 types of hoppings, 0, 1, and 2, depending whether the word is 0, 1, or 2. And we are going to do this by taking first to simplify just one parameter, which is the ratio T0 over T1, which is equal to T1 over T2. And we can now calculate the energies as a function of the eigenstates. And I can again see a very beautiful and symmetric structure, which is again a multifractal in the structure of the eigenenergies. And so this is specifically calculated for rho equals 0, 3. So there is a structure behind, there is still the same type of multifractality in the energy spectrum. And we can again do all this renormalization procedure to try to understand further what's going on. So here you single out all the words which are between ones, and you will see that they can be 0 to 0, or 0, 0, or just a single 0. And these different classes of words between ones are being painted in 3 different colors. This is going to be a very essential property for the renormalization, that you will map 0 to zeros into 0, 0 zeros into 1, and 0 into 2. And when you do this, you will get again a Fibonacci word. So you can now perform the same kind of calculations that have been done before for the Fibonacci, but you will now denote this T0 over T1 as a rho to P, T1 over T2 as a rho to Q. Then you can rewrite this Hamiltonian as an approximate sum of the scaled versions of itself, but they are not identical copies, as you can see here. And you can do the same decimation procedures, and you will see something very beautiful, that actually the fractal behind the Fibonacci word is the Rosy fractal. That was already known to be the case, that the Fibonacci word is connected to a Rosy fractal. And you can see that if you start with a word and you would start growing here in 3 dimensions, so you say that the x-axis is 0, y-axis is 1, z-axis is 2, and you could move in 3 dimensions, a step in each direction as you go along the word. And now what you will see is that each of these colors, 0, 1, and 2, are going to sit in one different sector of the Rosy fractal. So there is again order behind the structure. And if now I plot my eigenstate energies as a function of the site label, I am doing here for 0,3 and for 0,8. Again, there seems to be some hidden structure that doesn't appear very clearly in terms of the site labels of the usual Fibonacci chain. But now, look at what happens if we plot these eigenstates as on top of the Rosy fractal. So let's take these 5 eigenstates, one in each of these 5 bands that we are seeing here. And let's plot now this modulus of psi on the Rosy fractal. What you see is that there is structure, there is order. The eigenstates are forming an ordered structure in Hilbert space. Look at this. There is a pi rotation here. They seem to be symmetric. And it's even stronger. There is this reflection symmetry that's going through the center of the Rosy fractal. So how can we understand that? You can do even a further partition. Instead of looking at a single site, you can look at a neighborhood of a site. Now we paint in blue the 0 zeros, in red the 0 ones or the 1 zeros, And in green, the 0 2's or the 2 zeros. I will now get this rosy fractal. And now, if I plot this in this band, I'm plotting this eigenstate here on the rosy fractal, it's fully on the green, because the green is that part. The central is the blue, the big here is the red, the outside here is the green. And indeed, you see now it's completely the most strongly support on the red and weak support on the other colors. The central one has a very strong support on the blue, but the structure is fading away in a fractal manner on top of the rosy fractal. It's fractals on fractals. It's extremely beautiful, the structure in Hilbert space of these wave functions. So the psi on the rosy fractal is ordered. It's ordered by its local environment. It is reminiscent of the conumbering for the Fibonacci chain. And we can keep partitioning the rosy fractal again and again by looking now at a larger region instead of a bond. You look at 3 sites and you keep partitioning it further and further. And you keep seeing the structure on the rosy fractal further and further. So now here you see that you can keep subdividing and enumerating all local structures. Moreover, all this is connected to a very beautiful concept developed in Hamburg in the group of Peter Schmelzer, which is the concept of local resonator modes. Each site, although your structure is quasi-periodic, if you look in terms of the local symmetries, you can classify it in terms of local resonators and understand the structure of the wave functions in an analogous way, how we do here in terms of the positioning these fractals. So I would like to now then come to my conclusion. I have been telling you that structures like the Fibonacci chain, although they are not periodic, they are highly ordered. If you look at some impurity, a random impurity, it will lead to localized states, but this criticality will disappear with the number of impurities or the intensity of the impurity potential. But before this happens, you will find order within disordered. So there is a one-to-one correspondence between the number of the renormalized path and the type of disordered graphs. This order that we have been seeing in the Fibonacci chain is inherited in other structures, like, for instance, the Fibonacci. Now, if you are starting from a 3-dimensional structure and projecting in 1 dimension to get the Fibonacci chain, the transverse dimension, which before was just the conumbers for the 1D Fibonacci, now for the Fibonacci, the transverse structure is a plane, which is the rosy fractal. And when I project my wave functions onto this rosy fractal, I can see the underlying order of the multifractal structure of the spectrum. And I will see that on the rosy, my wave functions are forming a beautifully ordered structure, which is fading away as I go to the other colors in the rosy fractal. So I would like to close with an inspiration from a Swiss artist, Ursus Verli. So the Swiss are very famous for liking to order everything. So because of this cliche, Ursus has been playing around and ordering cars in parkings at supermarket, or ordering the room of the famous painting that we had, the Van Gogh painting for his room, which is completely disordered. He has been redoing the painting of Van Gogh with an ordered room. So basically, he would take a fruit salad and order to reveal which all the ingredients which are there. This is extremely nice because it allows us to understand what is it made of, what is in there, and how much of each one. But still, it's much more delicious to eat all of them together and to handle with the beauty of the quasi-crystals as they are. Thank you very much for your attention. Before finalizing, I put you again the photos of all the co-authors. Anwar Mustache, who did most of what I was presenting you for the Fibonacci's. The letters were in collaboration with Malte Röntgen, Christian Morphonius from the group of Peter Schmelher in Hamburg. And the work of Julius is co-supervised by Karma Dajani for the Fibonacci. And the first work of Anwar was also co-supervised by Sander Kempkes, who was a PhD student in my group at the time. And I thank you very much for your attention.